Can you see the screen? Okay. So we are going to start with the basic concept. Just a moment. Okay. So first thing first, what exactly is relation that you have learned in class 11 only. Okay. So relation means suppose like it's a just we are having a relation between a father and a son, and any two person in real life. Similarly, here we will be having relation between two sets. The concept of relation already you have learned in class 11. Here relation means a example of relation can be, just a moment, let me take one example. Okay, so an example of relation can be, let's say R is a relation such that consist of ordered pair all xy, set of all or xy where x is greater than y. This is one of the example of relation. Here the predefined set can be R such that A to B, where maybe A is given and B is given. So this is one of the example of relation we are having. Here A can be, we can take A as a, let's say 1 2 3, and B we can take as a, let's say 4 5 6. So this is one of the example of relation. Okay, here set A is there, we know the element of set A, we know the element of set B, and there is a condition which is defined over here, that relation between like set A and set B is one of the element of set A must be greater than the other element of set B. Okay, so this one is one of the example of relation. Cartesian product, if you will recall the concept of Cartesian product, the concept of Cartesian product was A cross B. That means 1 with 4 we used to take, 1 with 5 we used to take, 1 with 6 we used to take, then 2 with 4, 2 with 5, 2 with 6, then 3 with 4, 3 with 5, 3 with 6. This is how we used to take the ordered pair when we were finding Cartesian product in class 11. Okay, so we used to take 1 with 4, 1 with 5, 1 with 6, then 2 with 4, 2 with 5, and then 2 with 6. Similarly, we used to take 3 with 4, like all the possible arrangement we used to take when we were finding the Cartesian product. Now, whenever we are having a relation, it is just the subset of this Cartesian product. Now, here this one is one of the example of relation. If you will focus on this relation, you must be thinking this is an empty relation. Yes, it is. We will also be discussing about the types of relation mainly in this chapter. So the concept of relation must be clear to you. Let's say we are having the same A and B, and the relation can be defined as set of all ordered pair xy such that uh, y is equals to x plus 3. Okay, so this is also one of the example of relation. Here condition is mentioned. According to this condition, we will write down the set, we will write the set, we will write all ordered pair. Now here we are having few types of relations, and the types of relations over here are We will be discussing about, today we are going to discuss about empty relation. Today we will be discussing about empty relation. First one. The second one is universal relation. Third one is identity relation. The fourth type is reflexive. Next one is symmetric. Next one is transitive. And the last one is equivalence relation. One by one, we will be discussing about each and every type of the relation with the help of example. So let me take one example for empty relation. Whatever we have discussed, whatever example I have taken in the very beginning, that is a relation is R is defined as a set of all xy such that x is greater than y, where A and B is defined, R is from A to B, A and B is defined 1, 2, 3, 4, 5, 6. If you will write this relation, let me write it again freshly. So I am saying there is a set A, there is a set B. The element of set A is 1, 2, 3, and the element of set B, it's 4, 5, 6, and we are having a relation R from A to B, which is defined as it consists of all ordered pair xy such that x is greater than y. X is greater than y. If you will try making this, writing this relation in the form of like a set, if you will write down the element of R, x is greater than y. These are x and these are y. You can see x is greater than y. Those ordered pair only we can take it. Here, if you will focus, 1 is less than 4. 1 is less than 5. 1 is less than 6. So 1 is not like the first element from the first set is not greater. The next one, 2, again it's less than, 2 is less than 5, 2 is less than 6, 3 is less than 4, 3 is less than 5, 3 is less than 6. So we can say there will not be any element in this set according to the defined relation. It will be an empty relation. Are you getting it? Are you getting it, everyone? Now, what about universal relation? So for universal relation, the same example I am taking, just reversing the case. If I will reverse the case, we are having a relation R consists of ordered pair x and y such that x is smaller than y. X is smaller than y. Now, if we will write down the element, according to the defined relation, we will be having x has to be smaller than y. Such ordered pair only we can take. So the first one, 1, 4. 1 is smaller than 4. 1, 5. 1 is smaller than 5. 1, 6. 1 is smaller than 6. Then 2, 4. 2 is smaller than 4. 2, 5. 2 is smaller than 5. Then 2, 6. 2 is smaller than 6. Again 3, 4, 3, 5, and 3, 6. You can see we have taken all the possible arrangement from the two set. Okay. And this is called the Cartesian product between A and B. This whatever we have got over here, every element is there. We were having 1, 2, 3. We were having 4, 5, 6. All the possible arrangement we are having in this set. 1 with 4, 1 with 5, 1 with 6. Similarly, 2 with 4, 2 with 5, 2 with 6. Similarly, 3 with 4, 3 with 5, 3 with 6. So according to the given condition that x has to be smaller than y, we ended up getting all the ordered pair, which is equals to the Cartesian product A cross B. So this one is one of the example of universal relation. Universal relation. Universal relation means like the relation, the set, what according to the defined relation, whenever we will be writing the set, it will be the subset of the Cartesian product. Here, since we ended up getting the whole Cartesian product only, that's why we are saying it's the universal relation. Okay, so the first one, that is empty relation. Example I have given. What exactly is universal relation? Example I have given. I believe these two are clear to you. If not, please let me know. Now the third one is identity relation. Let me take one example of identity relation. Okay, so we can take let's say we are having a relation R defined on set A to A. Now, when we are going to talk about identity relation, reflexive, transitive, symmetric, here we will be discussing about there is a set A, which is just set A to set A. The relation will be always defined on A to A only, B to B only. Okay, when we are talking about identity, symmetric, transitive, reflexive, so this will, here we will always be having set A to A. Okay, and the relation will be defined like that only. Here we will not be having two different sets. So the example of this identity relation we can take as a, let's say we are having set A, which is consist of the element of set A is 1, 2, 3. Okay, so 1, 2, 3 we are having over here, and here also we are having 1, 2, 3. Now, according to the definition of identity relation, here every element must be related to itself. So the example of this one, like 1, 1, 2, 2, 3, 3. If every element, each and every element of this set are related to itself only, then we can say this is the example of identity relation. Identity means itself. Identity means the word. If you will focus on the word, you can understand uh, something which is related to itself, its own identity. So one will be related to 1, 2, 2, 3, 3. If this type of ordered pair we are having, then, and you must know that each and every element must be having this type of uh, identity relation with itself only. Then only we can say it's a example of identity relation. If we are having 1, 1 and 2, 2 only, then we can say it's not an example of identity relation, because the element of set A is 1, 2, 3. So every element must be having the ordered pair, 1 with 1, 2 with 2, 3 with 3. That's an example of identity relation. Now the next one is reflexive relation. Here basically we are going to discuss about reflexive, symmetric, transitive mainly. So reflexive is, let's say the same if we are having an example, let's say relation R defined on set A to A. Okay, and the same example we can take, the element of A is 1, 2, 3, and here if we are having R which is having 1, 1 and 2, 2 only. And one more thing I want to mention over here. For the identity relation, every element like the ordered pair must be 1 with 1, 2 with 2, 3 with 3. Okay, and no other element must be there. If we are having 1 with 2 over here, or maybe 3 with 4 over here, let's say 1 with 2 or maybe 2 with 3 we are having, if these elements are also there, then we can say it's not an example of identity relation. So basically in identity relation we will be having ordered pair 1 with 1, 2 with 2, 3 with 3, and no other element must be there. Okay, if there is another element also, there is another ordered pair also, then we can say it's not an example of identity relation. Okay, let's move ahead. Now for the reflexive relation, if we are having the same example, that is A is having the set A consists of element 1, 2, 3, and we are having a relation which is having, according to the relation, we are having 1 with 1, 2 with 2, 3 with 3, and also we are having 2 with 3, and also we are having 1 with 2, and also maybe we are having 3 with 2. If this type of set we are having, this type of ordered pairs are there, then this one is reflexive relation. The reflexive relation means each and every element must be having, like one must be having 1 with 1, 2 with 2, 3 with 3. So every element, what we can say, every element must be having relation with itself. This one we can say every element is having relation with itself. If there are another ordered pair also, that is perfectly fine. Okay, so if there are this type of ordered pair in the set, that is fine. This one we can say it's a reflexive relation. So in identity relation, there must be not like a different ordered pair. Every element must be having relation with itself for identity one, and for the reflexive one another ordered pair is also acceptable. When we will be checking reflexive, symmetric, transitive, then you will understand it in a better way, how exactly we are checking whether the given relation is reflexive, symmetric, transitive, and equivalence relation or not. Okay, let's uh, move ahead and let's talk about the next type, that is symmetric. Let me take one example. Okay, so according to this symmetric relation, if AB is there in the set R, then BA also must be there in the set R. Now, example of this one we can take, let's say we are having a relation R defined on set A to A, where the element of A, if I am taking again the same, that is 1, 2, 3, and if there are three examples I am taking, that is R1, R2, R3. We will be discussing what exactly is symmetric relation. So if we are having R1 as a 1 2, 2 1, 1 3, and R2 if we are having 1 2, 2 3, 3 2, 2 1, 1 1, 2 2, 1 2, 2 3, 3 2. If this three examples we are having, we will be checking whether this one by one, whether the given relation is symmetric or not. So I am saying if AB belongs to set R, then BA must be there in set R. Okay, so AB 1 comma 2 is there, then 2 comma 1 also has to be there, and yes, it is there. Okay, so we can say it's symmetric. Okay, 2 1 is there, then 1 2 is there. This two are symmetric. Now 1 3 is there, then 3 1 also has to be there in the set, in this set, but it is not there. So we can, is it symmetric or not? Anyone? Anyone? Is this relation is symmetric or not? It's not symmetric. Why? Because 1 3 is there, 3 1 also has to be there in this set. If since 3 1 is not there, then we will say it's not symmetric. Similarly, for the next one, 1 comma 2 is there, then 2 comma 1 also has to be there in this set. So I'm going to search 2 comma 1 is there or not. I can see it's there. So I can say this one is symmetric and this one. Let's check each and every element we will be checking. Okay. So the next element is this one. 2 comma 3 is there, then 3 comma 2 must be there. So this two also covered. Now the next one, 1 1 and 2 2, this one we don't need to check. Okay, so yes, it's fulfilling the criteria of symmetric relation, and we can say R2 is symmetric relation. This is symmetric. Whenever we are having 1 1 2 2 3 3 4 4, we don't have to check whether it is symmetric or not. Okay. Next one, R3, R3. The third example here, 1 2 is there, then 2 1 also has to be there, which I can't see over here. Then I don't need to check and go. I don't need to go ahead and check again. We can, here only we can declare it's not symmetric. Is it making sense to you, everyone? Are you getting it? Yes or no? Let me know. Is it clear or not? Let's move to the next one, that is transitive relation. So according to the definition of transitive relation, that is if AB belongs to set R and BC also belongs to set R, then AC must be there in set R. If AB is there and BC is also there, if AB is there and BC is also there, then and only then we will check about AC, whether AC is there or not. If AB is there and BC is not there, then we don't need to check it. So you can keep in mind, this is the first condition, that if AB is there and BC is also there, then and only then we will check whether AC is there or not. The next one condition you can keep in your mind, if AB is there in the given set, in the given relation, and BC is not there, BC is not there, then we don't have to check about AC. Okay, if AC is there or not doesn't matter, we will be not checking about AC. And this is the, we can say this two are the condition of transitivity. Okay, let's move, let's take few example. So here, yeah, Just like the previous one, if I'm having one of the example, another example, and the third example. So the first example, let's say we are having 1 with 2. The same A is 1, 2, 3. Let's say 1 with 2, and next one we are having 2 with 3, and the next one I am having 1 with 3. R2, if I am having 1 with 2, 2 with 3, 1 with 3, and 1 with 1. R3, 1, 2. Here also we will be focusing on each and every element of the set. So 1, 2 is there. 1, 2 is there. Then we will be checking A, AB is there. BC is there or not. This 2, is there any ordered pair which is starting with 2? So yes, I can see this is here. 2, 3 is there. So it looks like BC is there. So AB is there, BC is there. Then we will be searching about AC. Okay. So I can see AC is also there. So this is fulfilling the criteria of transitivity. Which one is fulfilling the criteria of transitivity? The first ordered pair, that is 1 comma 2, is fulfilling. Just by looking at this structure, that AB is there, BC is there, AC is also there, we can say it's transitive. No, focus on each and every ordered pair, you will never go wrong. Okay, so 1 comma 2, I am just checking for the first one. 1 comma 2 is there, then 2 to 3, 2 is going to 3, then 1 3 is also there. So the first one is fulfilling the criteria of transitivity. Still we need to check the rest too. Okay, now the next one, 2 comma 3 is there. Is there any 3 to something? So it's not there. As I said, if AB is there and BC is not there, we don't have to search about, we don't have to look for AC. Okay, so this is also fulfilling the criteria of transitivity. Now the next one, 1 3 is there. 3 to any other number, is it there? It's not there. So if it's not there, we don't have to think about any other thing. We can say it's transitive. Are you getting it? So in total, it's transitive now, I can say. Clear? Now the next one. First, I'm going to check this green one. Okay. Accordingly, we will declare for the green one. 1, 2 is there. Then 2, 3 is also there. As I can see over here, 2, 3 is also there. We will search for 1, 3. Yes, it is there. So hence, the first one is fulfilling the criteria of transitive. Let's see for the other one. 2, 3 is there. 3, 3 to any other number is there? No. So this is also fulfilling the criteria of transitive. So basically, I am saying that if AB is there and BC is there, then we will search for AC. If AB is there and BC is not even there, BC is not there, then we don't have to think about AC. Okay. So here for the second one, 2, 3 is there, and 3 to any other number, it's not there in this set. So we don't have to think about AC. Okay. This is transitive. The next one, 1 comma 3, 1 to 3 is there, 3 to any other number is not even there. So this is fulfilling the criteria of transitive. 1 1 is there. Whenever we are having ordered pair like this, 1 1 2 2 3 3 4 4, don't just don't don't focus on that one. That is transitive, that is symmetric. Okay, so this one is transitive. So we can say this is also transitive. Is it clear? Is it clear? This way only we will be doing it. Just a moment. Now the last one, 1 comma 2 is there. So no other element is there. So definitely we will say it's a transitive. Any confusion? so far? Anyone having any confusion? No? Now the next concept is, if let's take question from this concept, that is how to check whether the given set is reflexive, symmetric, transitive or not. And yeah, when any set is fulfilling all these three criteria, that is, it is reflexive relation also, symmetric also, and transitive also, then we will say it's an equivalence relation. Now let's take few questions. So question number 1, we are having, let R be the relation on the set 1, 2, 3, 4 given by R is equals to, I am writing the set over here, the elements 1 comma 2, 2 comma 2, 1 1, 4 4, 1 3, 3 3, 3 2. Therefore, option A, R is reflexive and symmetric but not transitive. Next one, R is reflexive and transitive but not symmetric. Other one is R is symmetric and transitive but not reflexive. The last option is R is an equivalence relation. Let's check it. Let me know, write it down in the comment section whether the given set is reflexive, symmetric, transitive, which option is the correct option. Check it and let me know. No ma'am, for which, for what you have answered, no. It's clear, not clear? Okay, no confusion. Okay, answer it please. Everyone, I'm expecting answer from each and everyone. Okay, let R be the relation on the set, this one, given by set R is mentioned. This is the very basic question. Why? Because here you can see the set is given. The element of sets are 1 2 2 2 1 1 4 4 1 3 3 3. So here doing this type of question is very, like, it's comparatively easier when we are having the set like set of natural number to natural number, integer to integer, real number to real number, and then a relation will be given in that manner. We will be taking those example. There we have to think a bit, but in this type of question we don't even have to think, right? Is it reflexive, symmetric, transitive, reflexive and transitive but not symmetric. Everyone, is it so? Reflexive and transitive and not symmetric. Reflexive, as we can see, 1, 2, 3, 4. So yeah, it's reflexive. Symmetric. So 1 with 2, then we will be searching 2 to 1. It's not there. We don't have to think anything else. Okay. We don't have to go ahead and check for each and every ordered pair. No. If one is not fulfilling the criteria, we can say it's not symmetric. Now transitive. So 1 to 2. Is there any 2 to any other number? No. So we will say yes, it's fulfilling transitive. This is also fulfilling, this is fulfilling, this is fulfilling because these are just the ordered pair, the same element with itself. 1 is going to 3, 3 is going to no other number. So yes, each and every element is fulfilling the criteria of transitivity. Okay, 1 is going to 3, 3 is going to 2. So 1 to 2 must be there. Yeah, it's there. That is transitive. 3 is going to 2 and 2 is going to other number. No. So yes, it is transitive. So option number R is reflexive, symmetric. No. Yeah. Option number B is the correct option, right? Right? Everyone is getting the same. Let's move ahead and let's take few more questions. So suppose we are having the question as let R be the relation in the set N given by R is equals to set of ordered pair AB such that A is equals to B minus 2, and also there is one more condition that B must be greater than 6. Choose the correct option. This question I have taken from the previous year question paper. So number A, 2, 4 belongs to R. B, 3, 8 belongs to R. C, 6, 8 belongs to R. And D, 8, 7 belongs to R. So there is a relation R defined on the set N, that is natural number, given by the condition is given, that is R consists of all ordered pair AB such that A is equals to B minus 2 and also B has to be greater than 6. Which option is the correct option? The element of R. Which one is the element of R which is fulfilling this criteria, the condition given for the relation? Here it's given that A is equals to B minus 2. Okay. So B minus 2, this is fulfilling. B minus 2, no, it's not fulfilling. B minus 2, it is fulfilling. B minus 2, it's not fulfilling, right? Now another one is given the condition as a B must be greater than 6. So B must be greater than 6. So here for the first one, it's not greater than 6. The option number C is the correct option. Can we say? Which is fulfilling this and this, both the condition. Is it clear? Now the next question is, check whether The relation are defined in the set 1, 2, 3, 4, 5, 6 as R is equals to set of all ordered pair AB such that B is equals to A plus 1 is reflexive, symmetric or transitive. We have to check it whether it is reflexive, symmetric or transitive. Okay. So R is given, B is equals to A plus 1. So reflexive, what does it say? Just a second. Now the condition of reflexive says that the ordered pair A comma A must belongs to R, right? And here it's given that B is equals to A plus 1. According to the reflexive condition, A must be equals to A plus 1, which will not be true for any number. Natural number, integer, real number, any number, A is equals to A plus 1. It is invalid equation. According in mathematics, 2 is equals to 3. It's completely invalid. So we will say it's not reflexive. Okay, A comma A doesn't belongs to R, hence not reflexive. Now we will be checking symmetric. So what does the condition says? If AB belongs to R, then we have to check BA must belongs to R. Okay, AB belongs to R. Then let's see AB belongs to R, which says that B is equals to A plus 1. Now B comma A must belongs to R. If this belongs to R, then the given relation will be A is equals to B plus 1. If B is equals to A plus 1, then we cannot say A is equals to B plus 1. Okay. Basically, from here, A will be B minus 1. A will not be B plus 1. Okay. So we can say B comma A doesn't belong to this relation and hence not symmetric. The given relation is not at all symmetric. Are you getting it? According to the given, from where I am writing this thing, you can focus over here I am copy pasting this one, that according to given ordered pair, if AB belongs to this relation, then B must be equals to A plus 1, and when we will solve it, we will get A is equals to B minus 1. But the condition of symmetry says that AB belongs to R, then BA must belongs to R. If BA belongs to R, what does that mean? BA belongs to R, that means the given condition, according to the given condition, the second one B is equals to the first one, the first term, the first element plus 1. So I have taken the same, the second one is equals to the first element plus 1, which is not true. These two are completely different, you can see. That's why it's not symmetric. Is it clear? Now we will be checking the transitivity. Let's check it. Transitivity we will check. So what does the condition says? If AB belongs to R and BC also belongs to R. So if AB belongs to R, the given relation says B is equals to A plus 1. BC belongs to R, that means the condition says we can write it as C is equals to B plus 1. Then we have to check whether AC also belongs to R or not. AC belongs to R means what? AC belongs to R means what? The condition was if AB belongs to R, then B is equals to A plus 1. If we will focus on this one and if we want to write it in terms of AC, we can write C is equals to A plus 1. This is what we want. If we will get this one, then we can say AC belongs to R. Right? Right? From here, if we will substitute the value of B, if we will substitute this value of B over here, because we want a equation, we want a relation between A and C. So B we will be eliminating just the way we solve the equation. So if we will substitute B A plus 1 at the place of B, if I am substituting A plus 1 over here, C is equals to, what are we getting? A plus 2. What we want C is equals to A plus 1. Then and only then we can say AC belongs to R. So can we say it is not transitive also? Can we? Yes or no? Let me take another question. Let me know whether it is clear or not. It's not transitive. That's what I am saying. This is how we will be solving the question in this chapter. The question will not be that straightforward, like 1 comma 1 is there, 2 comma 2 is there, 2 comma 3 is there. Then we will be checking whether it is reflexive, whether it is symmetric, whether it is transitive. However, we could have done this question like that by applying the basic concept, by writing all the ordered pair, and then we could have checked whether 1 1 is there or not, 2 2 is there or not, 3 3 is there or not, 4 4 is there or not. We could have done like that, but this is the standard way of doing question. Like basically most of the question from this chapter we will be doing like this only. Let's take another example. Yeah, one of the most important example or important question from this chapter is show that each of the relation are in the set A is equals to x belongs to z such that given by R is equals to set of all ordered pair AB such that mod of A minus B is a multiple of 4. Is an equivalence relation. So we need to check whether it is reflexive, symmetric and transitive or not. So for reflexive, what we will be checking? A comma A must belongs to R. A comma A means A minus A, mod of A minus A must be a multiple of 4. Mod of A minus A is what? 0. 0 is a multiple of 4. Yes. We can say 0 is a multiple of 4. Yes or no? We can say 0 is a multiple of 4. So hence we can say it's a reflexive relation. Now the next one, symmetric, if we will be checking. So A comma B belongs to R, then we will be checking whether B comma A also belongs to R or not. B comma A means the first element minus second element, it is written over here. So that means first element minus second element. If this is true, then we can say it's symmetric. So yes, this is true. Mod of a minus b, mod of b minus a is the same thing. Modulus inside the modulus, a minus b, b minus a, definitely whatever will come out, that will be positive. So whether we are doing 2 minus 3 or we are doing 3 minus 2, we will end up getting the same result. So yes, it is symmetric also. Now we will be checking the transitivity. So if a comma b belongs to R, b comma c, b comma c also belongs to R, b comma c means mod of b minus c, this is also belongs to R, then we will be checking whether a comma c belongs to R or not. Anyone from here, let me know whether it is transitive or not. Let me know. You have already done this chapter and a lot of time. You have also given the test from this chapter. Like revision also you have done. And in exams, like in exam also you have given exam, and definitely this chapter was there. So this chapter you have just like done a lot of time. So let me know whether it is transitive or not. Who will be saying? No one. let's say we are having let's say we are having this modulus of a minus b, that is a comma b belongs to us. So modulus of a minus b, if I am saying it's a multiple of 4, so we can take 4 and, right? And b comma c also belongs to R, so modulus of b minus c, this is also a multiple of 4, because we are saying this is true and the other one is true, then we are checking a comma c is true or not. So this we are saying, let's say it is 4n, so a minus b will be plus minus 4n, and b minus c will be plus minus 4m, right? If any number if is there inside the modulus, that can be positive, that can be negative. Okay, so a minus b will be plus minus 4 and b minus c will be plus minus 4m. Now we want to see the relation, we want to check whether ac is true or not, ac is true or not. Okay, so b is here, b is here, we want to eliminate b. In the previous one we have done the substitution to do just to eliminate. Here we will, if we will add this two equation, we will be able to eliminate b. So a minus b plus b minus c, if we will be doing here, we will be getting plus minus 4n, and here also plus minus 4n. So plus minus 4, if we will take common, if we will be having n plus n over here, and here a minus c we are having. Can we say yes, it is transitive, because a minus c is equals to plus minus 4 and plus n. It is a multiple of 4, as we can see. A comma c is fulfilling the criteria. So it is a multiple of 4. Mod of a minus c, we can say from here, is a multiple of 4. And hence it is transitive, right? Clear? Is it clear?